invitation to the committee, scientific committee and organizing committee. As mentioned by Professor Mohi, I'll talk about ammonia. Bear with me, please, the first 20 slides, because I want to set the mood on why we want to use ammonia. So it's going to be a very quick skip, and then after that jump into what is the part of combustion that is interesting. And also, I haven't slept in 30 hours because we had an issue in London. But again, if you hear me saying something odd about ammonia, it could be that it's not 30 hours or that I probably smell it. So I don't know what it is, but it's something along those lines. So introduction, challenges, developments that we got in Cardiff, some other institutions as well, collaborations, and then finally conclusions about this subject. So just continuing with the subject before we solve all the technical issues. I remember how all this started, and it was just a few days before Christmas in 2013, where Siemens showed up saying we want to burn ammonia. And I remember my group leader, Phil Bowen, for those that know him, yes, went, why do you want to burn ammonia? So first things he said was, well, don't take or pay a lot of attention to this. It's probably one of those Cinderella projects. So again, it's not going to then give us anything or give us any research. It's just probably one project we can do here or there that will do the trick. So I thought, okay, why not? Let's do it. This is an updated version of what I passed to Professor Mohi. It's a few months that I passed it with that. So things have increased, the amount of papers just gone much higher, and projects as well. So it's one of those subjects that people are getting really interested in, naturally following. So as I mentioned, please bear with me, next 15 slides, so I can then just kill them in a few minutes. But essentially is that we know what we're doing this, we have all this intermittency coming from all renewables, and we need a way to store all that energy that we have available. Chemicals, among all the different methods to store energy, are probably the ones that we know how to use better. We have been employing them for millennia, and in the same way, we can then use and store as much energy as in gigawatts over months, years, and decades. So it's a very good and very convenient way of actually doing it. And as we know, hydrogen is the one that everyone is talking about these days. Now, this, what you can see, is the promise. The promise is that in 20 years, 30 years from now, hydrogen obtained via renewable energy is going to be much, much cheaper than the one that we obtain using conventional methods of stimulating reforming. Therefore, this is probably what we've been solved across all the different media. So in that sense, all countries that are trying to reduce their carbon footprint, they have defined what they own net zero strategies. Here, for example, I'm showing the one from the UK, where we talk about electrolysis, carbon capture and storage, some mobility of CO2, and then use those vectors to produce power, energy, heat, cooling, etc. And one of those is obviously ammonia, when we talk about the conversion. The conversion of these renewable energies. In Wales, we have as well our own strategy, and then the strategy goes from 2020 to 2030, then into net zero, transportation, power stations, and then clusters all across the south, the north, and across the valleys. So therefore, and it's just one of the many, many different plans that countries like Wales have. Now, something that is really interesting is this analysis done by the Hydrogen Council just a couple of years ago. And it shows, first of all, that most countries around the world, they do have the potential to produce these renewables. That's in the case, when we got natural gas, they're very localized. And that we know that's the reason because we can exploit it. One of the things that they tried to do was to then analyze, okay, if we're going to produce all this hydrogen, how are we going to move it around? So places where it's produced can deliver to places that is highly needed. And just for the analysis, what they did was to then compare the cases of Chile to the US, Saudi Arabia to the European Union, and then Australia to Japan, looking into 3 different vectors that are commonly used or commonly in research: ammonia, liquefied hydrogen, and liquid organic hydrogen carriers. And something that comes out very interestingly is that as we start the production to the cost at port, they're barely the same. Okay, $3.5, $4.4 per the kilogram of hydrogen. Now, one of the things that is really interesting and I want you to focus on is this bit, the cracking. So this analysis on the cost looks into the almost a third of the total cost from production to port using ammonia when it's cracked. But what if we reduce these components? What if we just avoid using cracking? Therefore, we'll make the best option for long distance and long storage delivery of hydrogen, ammonia in the case. Therefore, ammonia is a fascinating agent, a chemical that can be obtained from renewable energy, stranded resources, waste streams. It is much cost effective when you're talking about long distances or long periods of storage, calculated around 30 times difference between one and the other, because we obviously need to high pressurize or then cryogenic go into hydrogen storage. We can then produce it in islands or locations where we are far away from the grids. It's also obviously used as a fertilizer, but now we're talking about using it as a fuel. Contains more hydrogen than hydrogen itself because it has 3 atoms of the molecule. And then finally, there's 150 years of having ammonia moving around at around 200 billion euros per year. And that makes it a fascinating again, method to then store and move hydrogen. And as you can see, one of the highest compared to many other materials that have been then assessed over the years. So on those lines, where is this going? Well, first of all, we have the brown or gray ammonia that is produced via conventional methods. We want to avoid that. We want to reduce the CO2. Where we're moving then to then green ammonia that is going to be produced using all these renewable energies via electrolysis, which makes the production of hydrogen still very expensive. And then finally, the dream of trying to avoid that electrolysis and then using surface materials or any interesting method, then produce the ammonia straight away using water and nitrogen. When that happens, probably the next Nobel Prize will be granted, and we'll have an economy that potentially can be based on ammonia. So therefore, there are a lot of different methods and different ways of using the chemical, and it is a potential for transport, heat, cooling, process industries, propulsion, and stationary power. But there are still many things that we don't know about and that we need to fully understand. Reaction and combustion is one of them, and I'll mention about that. Public perception, a massive and important point. Regulations, we don't have any regulations to move ammonia as a fuel jet. Economics, they need to then make good sense, especially if we're investing in them, and then obviously the environment as well, we don't know how is that going to play. Comparing just the different cases of net zero and carbon-based fuels, what we got are cases where we have ammonia with a high energy density of energy per volume. And it shows higher than hydrogen. Therefore, when we're talking about shipping, rail, or lorries that are heavy duty or long distance, then having it as ammonia makes sense for the final cost. So it's going to be part of those that mix of fuels that we'll have in the future. This is some study done by the University of Louvain, where they analyze the conversion of renewable energy to then final use as power or electricity. And as you can see here, compared to the other cases where we have ammonia and carbon-based fuels, the 24% comes really close to the one that we got here for methane. Now, we need to then focus on this part of the storage. That is the one that is probably taking most of the efficiency, but again, is something that allows then have a good comparison between the cases. And finally, one of the things that was very interesting and that shows that both of them complement each other was this study done by Minnesota, where what they did was to analyze the levelized cost of electricity and then assess all these different cities across the states. And one of the things that they found was that there were some cities that would be more inclined to go for ammonia, more others for hydrogen. But when both were combined, because the reduction of renewable energy systems and storage facilities make the best case, because capex will be reduced, and therefore this shows that if we want to use energy from the summer over the winter, probably the best way to do it is using ammonia. So therefore, from that, the International Energy Association recognized finally the chemical as a fuel in 2018, and many different programs across the world. Europe, we have in Saudi Arabia, we have in Japan, that is the one that is pursuing all these, in the States, in Canada, etc., that are just going on ammonia. And on those lines, we have now new investments going in the billions, for example, for the New City. In the cases of Australia, they have ditched the use of connection lines, electrical connection lines, to then use ammonia that you can then deliver wherever you want, depending on the market, new green plants, and facilities for storage. And when it comes to combustion, General Electric and IHI, one of the largest industrial manufacturers in Japan, are just signing agreements to then use ammonia as a fuel. In a similar way that Mitsubishi is about to then commission a 40 megawatts power unit for pure ammonia. Similarly, marine engines will be probably the ones that see the onset of this fuel as the first large market. And it's not only that, but also we have engines and gas turbines already running at 2 megawatts power. We have concepts that show that we don't need to actually go onshore, offshore. We can then produce all these chemical and then ideas that are using ammonia co-firing with coal to replace coal in large power stations. Again, talking about 500 megawatts power already in the demonstration stage. And one thing that is interesting, aerospace applications, one subject that is still is in debate, now being looked at by Boeing and NASA into how they can use ammonia to then distribute that power. Developing countries as well are doing their part. Many other places like Mexico, Chile, Morocco, here in Egypt, and many other locations are actually looking into this net zero fuel as a big potential to then decarbonize the world. Why? Because we have its potential use in all these different applications, fuel cells, internal combustion engines that are of interest for us, combined cycle gas turbines, furnaces, and boilers, with all the different efficiencies and all the different pros and cons that you will have, again, that we are, especially in the area of making all this happen. So to make that, we need to focus primarily on 4 big challenges. The first one is that ammonia needs to be produced cost effectively. The second one is that the power generation utility scale, it needs to be clean, it needs to be stable. Public acceptance is a massive issue, and it's because people still don't believe that ammonia can be used. They say it's toxic, it's a nuisance, it's smelly. It is, but it has been used for 150 years as a refrigerant and also as a fertilizer. And the amount of deaths that we get over the last 50 years in developed economies is less than 100 in that number. An economy, finally, needs to be a profitable scenario to make all this happen. So as part of that, we have a Center of Excellence on Ammonia Technology that has managed to then work on all these different aspects, working on Royal Society policy briefings, some program grants, publications, and some books that we already got. And what has been the stuff and the research that we have done, especially in combustion-based technology. But initially, when we started looking into the propagation of the flame using a constant volume chambers. Was our first experiment when Siemens came over that cold winter. And when we thought about using it, we initially thought, let's find the right blend that would be close enough to that one of natural gas. So from that, and things have progressed. Many research topics and many universities have looked at it, and I'll show you now some of the results that they have found. Interestingly, one of the things that now are looking at, this one I read from China, looks into this propagation of the flame and how, depending on the pressure and the amount of hydrogen that we got, we obtain different profiles. And as you get obviously closer to the hydrogen, because of the low Lewis number, you will start seeing all the cells that are produced because of that parameter. But the interesting thing is that as we increase the amount of ammonia, then that goes down. So again, showing that somehow we have some more stability when we have an increase in ammonia. Now, as I'll show you later, once that we start using or increasing the turbulence, what will happen is that will be the other way around. So there's a point where we can then increase the amount of hydrogen to a certain extent that both of them will work together. These are some of the experiments that we initially did to then find out what was the laminar flame speed using those combinations, and we found out that 45% hydrogen with 55% ammonia would be the one that was closest to the methane. Now, one of the things that I'll show you later is that although this was in that bomb the case, then when it comes to the natural gas turbines, it's not the case, or turbulent combustion. Similar work done by the University of Orleans shows all the different changes in laminar burning velocity as we increase the ratios of methane and hydrogen. which is obvious, as we know that ammonia is a very dull, slow chemical. But something that was really interesting in the research that I did was to find out that when we mix around 20%, between 0 to 20% hydrogen or methane in ammonia, then the properties of laminar burning velocity are quite close. Meaning that if we are running a gas turbine, say, on pure ammonia, and then we want to then switch or add hydrogen or methane to then improve its combustion properties, then 20% could be the one to go for. Because finally, it's not seeing that difference, at least in the laminar burning velocity. So it's something that we can exchange in between one and the other fuel. These are some of the results that they obtained as well, looking into how the different turbulence exposed to the kernel will then produce changes in the propagation of the flame. And as you can see here, and we have the 100% ammonia, the flame becomes very unstable, unhomogeneous, and then heterogeneous. Well, as we start increasing the hydrogen, then that settles down, and then we got a nice propagation as we increase it. But there's a point, as I showed, where we start then having all these instabilities for the increase of hydrogen that takes over the reaction of the ammonia. Similarly, some studies done by DNS calculations by Hoven as part of our Flex Confu program has shown that as we increase the amount of hydrogen and also the equivalence ratio, then the properties of the kernel as well change drastically. So here in this case, for example, 0.8 equivalence ratio, 1 and then 1.2, and you see how the wrinkles go down. Similarly, as we increase the amount of hydrogen from top to bottom, just shows how that increase in hydrogen is a negative effect. These are some of the results that, as well, the University of Orleans are going to publish, and fascinating the analysis that they have been doing, working and then playing with some acoustics with a fundamental flame. And it shows as well, once that we have the curvature of the flame, increases the reactivity of what we got there in that scenario. Which is again something useful, because finally we can use that increase in reactivity to then boost some of the reactions that can reduce some of the emissions that we got in that field. Internal combustion engines, that's another area that we have worked on. We have a demonstrator in Oxford. For some of you that went to Cardiff over the summer, you probably have seen it. And we used to work on this internal combustion engine, hydrogen and ammonia. As we increase the amount of ammonia, as you get here, then obviously you reduce the CO2 emissions. But at the same time, as you increase it even further, you reduce the NOxes that are emitted to the atmosphere. And this is because ammonia is a fascinating denoxing agent used in catalytic systems, diesel engines, and is one of the main chemicals that bring down the emissions in power plants. So similarly, in that way, we went for 3 different combinations using natural gas that would just start the engine, then start putting some hydrogen and ammonia together, and eventually just replacing the natural gas to then get the power output. On that line of thoughts, we as well have been working on different concepts, and the idea goes behind this public perception of ammonia. Where is it conceived as a benign, good chemical? Usually because of, and something that I'll show you later, is that people in the farming sector, they're used to the smell, they're used to then deal with ammonia coming from waste, animal waste. Then these are the potential commercial venues. And on that line, what we are trying to do is work on different concepts for heat, cooling, stationary power, heavy duty, using pure ammonia. Whereas that we get the transportation and distribution of that ammonia to, say, for example, locations that we call now city gate terminals, similar to having high voltage terminals. We can then use the cracking devices to then provide for hydrogen to the city. That then, at the moment, is against the use of ammonia because it's a nuisance, it's a smell. So this is a program that we got running on marine engines, and one of the things that is important to notice is that we got, apart from all the fundamentals analysis, fuel atomization, and sprays, the part that is the acceptance. Acceptance, a major problem because of the legislation and the socioeconomics that relate to the use of ammonia that we don't know about. Boilers and furnaces are other technology as well that can be used very nicely when it comes to ammonia. And it's because, as I mentioned, it has the power to then deliver energy for these processes. Here is a unit that was developed a few years ago by the company Deuter. And what it does is consume ammonia from oil refineries. So essentially it goes into two-stage combustion and then eventually reduces. That way the emissions, they claim that the emissions have been very well below to the ones that the legislation allows. And this, I believe, is true. And I'll show you now why. So here as well, some analysis on the economics using not only these combinations of ammonia coming from oil refineries, but also propane that is very close in terms of storage to ammonia. So this is an analysis that we did just recently as part of a project that is targeting 2 megawatts power with the company Flowgas. And it shows that it can be replaced and it provides power, for example, here in the steel industry, from waste over 5 megawatts coming from that ammonia. So some of the work that we did experimentally was allowing us to then observe how humidifying these atmospheres could change the point of balance. So as I mentioned before, we have ammonia that can denox the environment where we're burning actually all these fuels. But there's a point that if we increase too much ammonia, then we'll have obviously ammonia coming out from the stack. So there's this balance, this point of inflection, where we can then even reduce it even further using humidification or injection strategies, and reduce as well the NOxes that we're producing. Another area that's really interesting, plasmas and liquid injection. This is something that has just taken a couple of papers, I think less than 10 for both topics in terms of ammonia. And it's really interesting to see as well that it's been Japan leading, especially with the injection of ammonia liquid. Has its perils because finally as we increase the amount of ammonia, then we increase obviously emissions coming out of the stack, not only the ammonia, but also then some of the NOx emissions that we got, because we're cooling down the flame process that again produces a lot of N2O. But the idea of using liquid ammonia is that we avoid the vaporizers. So avoiding the vaporizers will bring up the efficiencies and in that sense help us out to then deal with weathers that are difficult to control. One of the main issues that we always suffer, especially in the winter, is to then use ammonia in our combustors. And the reason is that, again, ammonia cools down and liquefies at very high temperatures, around 10 degrees at a bar, and when it comes to the atmospheric, minus 33 degrees. So being at 0 or minus 5 doesn't help. So having this liquid ammonia injection can then make the difference. And it's very easy to then liquefy. It's how it's moved worldwide and can be used directly as a method of fueling engines. They have done it using gas turbines. Oxford University is looking at gas turbines of 100 bar, and in the same sense, there are many institutions looking into internal combustion engines using this method. Plasmas, another subject. It was really nice to see Georgia Tech developing this system in the same way that some other universities, KAUST, Technion, some guys in Birmingham are looking into how we can then improve the combustion using this concept. And essentially we're producing radicals before they actually get to oxidize. So if that's the case, we have the potential to then produce a radical NH2 that is one of the parts of denoxing all these atmospheres. So NH2 is the radical to look at. Laminar flame speeds show how using the plasmas can change depending on the pulse energy that we employ. And in that sense as well, flame thickness shows a reduction and then an increase on the basis of that pulse energy. These are numerical analyses on the now experimental studies to validate, but then it shows that as well plasmas, they have a play to again a role to play in this area of ammonia combustion. And now getting into ammonia gas turbines, that is the area that we focus on the most. We started with these blends of high methane medium ammonia 3366, and that's when we saw the changes in always radicals. And one of the things that we saw, as I mentioned before, is this reduction of NOxes as we increase the covalence ratio, because essentially the ammonia that we're onboarding is reducing the NOxes. And the amount of NOxes that we're measuring is in the 1 digit, so 5, 6 ppm. Now the problem is obviously you have then ammonia going up, which means that we need to find ways to then improve or then design new injection systems that will allow us to then reduce that onboard ammonia. When we start looking into that 45-55 blend that I mentioned before, one of the things that we've observed was that we ended up with 2 envelopes of flame. So you can see here as a photograph where we have that almost invisible hydrogen flame surrounding the one that is the ammonia on the inside. And that, once that we did some numerical analysis, we found that as well, and it showed how the hydrogen is overtaking the ammonia combustion. So that's, again, one of the reasons, because there's a blend there that shows the best profile once that we start mixing both chemicals. Not enough ammonia that it will be too dull, or not too much hydrogen that will overtake the whole combustion. It's a mixture of them. And what we found as part of this was that 70-30, 80-20 were the potential ones to look at. And interestingly enough, during the time that we were presenting this in Dublin a few years ago, the guys in Tohoku, they were presenting as well the gas turbine, saying we have a similar idea and we're finding exactly the same thing. So what we're trying to do is use RQL technology, rich quentin, and then eventually produce at the very rich part this process of reduction of NOxes. And one of the things that happens is that we produce great amounts of hydrogen. So essentially, we thought initially that it was hydrogen that wasn't being born, but again, it doesn't make sense. And as we were doing some of the analysis, we found out that it was actually all this recombination of the species that will then produce all this amount of hydrogen, which can then be born in a secondary zone to then complete the combustion. Now, these are the concepts that we are now trying to target. CAUS is looking into the lean combustion side of the spectrum, which has its own challenges, but it's a fascinating area, again, trying to then discover what is the best combination to then burn the chemical. So here is what will happen. We have the rich combustion, then loads of air coming in, and then finish it to then burn out all that hydrogen that we're just post-producing here in this area. And why are we doing this? Well, essentially is that we have these scenarios. These are some studies done by Oxford University where they did techno-economics of having pure hydrogen being cracked fully, then these combinations of 70-30, and then finally ammonia. And as you can imagine, the less cracking that we produce, higher efficiencies we got. But then as I mentioned, the problem is that having pure ammonia can be dull, or having just pure hydrogen difficult to handle, as we know. So there's this combination that can give us somewhere around 60% if we know how to then use some of the properties of ammonia, like cooling, for example. This, as part of that analysis that they did, they compare an 80 megawatts power unit and an 870 power unit, and this is the amount of hydrogen that you would need to then run them for, say, 1 hour, 1 day, 1 week, or 1 month. Let's take just the example of 1 month hydrogen of the 870 megawatt power unit. Then, according to their calculations, we would need 2,500 kilometers of a 1.4 meter diameter pipeline. So again, possible that compared to just 2 big concrete storage facilities of ammonia, each of them capable of storing 50,000 tons each. As part of that, we did some calculations, some 3-generation analysis, because ammonia is a fascinating cooling agent, so we can put it as well as part of the whole process, and in that line, then increase the power output. So we can get cooling, power, heating at the same time in the range of what we have calculated, 60% compared to 80. That is probably the best and most advanced combined cycle nowadays. These are some of our facilities where we're doing some of these tests, where we have different systems for high pressurized conditions and some others for fundamental analysis atmospheric. And on those, we managed to then get some of these analyses, different temperatures, different equivalence ratios, and the one that is interesting is this one that looks into how the flame has retreated and then increased its reactivity as we increase the inlet temperature. Now, one of the things that we found as we were doing some of these chemical analysis was that the combination, and here we have some that is at atmospheric conditions, and one that has an inlet temperature that is very high, and it shows that at the flame front, the profiles of the chemistry are pretty much the same. So this one compared to that one is almost the same. But then what happens is that as we go down the line, what happens is that we got then the post-combustion zone making a huge difference between one and the other. So it's the post-combustion, the one that we are targeting. As part of that, looking into the radical formation of all the species that we got and the different combinations that we have, we got all the different species, OH, CH, NH, and NH2, and how they decrease or increase as we change that amount of hydrogen ammonia that we got. So the blend that we got at 75-25, that is the one at the very bottom with ammonia and hydrogen, shows that NH2 radical that I was telling you about, that if we combine with NO, would give us water and nitrogen. That's the reaction. Now, the problem is how to boost it and then avoid the formation of HNO, that is the predecessor of NO in this combustion problem. Another thing that we did was to then evaluate the position of the flames. So it shows that there's a trend as we increase or decrease that amount of hydrogen. And again, it shows that in most of the cases, CH, NH, and OH, they go up, but then NH2, they get closer to the nozzle. So again, a way of how we can then produce it in a way that we can use it for destruction. Some numerical analysis that we have done over the years, and it shows the formation of vortices and how and where we have all this formation of NO that is for the residence time. But as well, it's one of those cases that if we manage to then get it right, and the timing and the condition tuned, at the temperature and the amount of ammonia that is required, we can then target those regions as the place where to inject that onboard ammonia, or how to then get it. And in a similar way, the instabilities that could happen in the system, consequence of that hydrogen that we got. Now, one of the things is that as we run on rich conditions, obviously in thermoacoustics, they disappear, but then in that secondary area where we got all that hydrogen very lean conditions, then the story changes. Some other analysis that we have done show these ternary blends, as I showed you when we were running the internal combustion engine, and how it would just change that profile and operability. And another thing that we still don't understand is once that we start mixing them, then they change the profile of NO, NO2, N2O, and ammonia as we then increase. Well, one that we found that was really interesting was 20-55-25 methane ammonia hydrogen. And it's got to do probably because a combination of extinction strain rate and a combination as well of the reactivity between all these molecules. We don't know, and it's one of those cases that we think, for example, in the cases of Egypt, that will be probably running on natural gas and eventually replacing it slowly with ammonia and hydrogen. They will have, at some point, then these ternary blends. So it's something worth looking at. Another thing as well is using stratification. That's something that we have tried. And it shows, again, that we target them properly. That location of NO formation using this NH2 that we have produced, then we can then reduce substantially the NO that is formed. So that's one of the ideas that we got, and as well some other groups worldwide are looking at it. Kaust and us, we did this in collaboration, was really interesting and presented in the Proxy Institute, and it shows how targeting all the different radicals, there's a trend using spectral analysis, a trend that can be employed not only to know what is going on in the field, but also to then use a system for health and safety. Another thing that hasn't been mentioned, and as well is now picking up very slowly, but eventually will have a big consequence, is how the ammonia-hydrogen blend will impact on the materials. Because finally we'll have hydrogen that can brittle and nitrogen that can nitrate. So as we did some experiments, what we tried was high temperature materials and expose them to these atmospheres. And what we found in collaboration with UCL was that we had embrittlements. So how much is too much, we don't know yet. Flex and Confu is another project that we got going, and this one shows how we can use off-peak power to then generate ammonia, eventually tank it, and then use it directly into the turbine during peak time, or then crack it to produce the combination of nitrogen and hydrogen. And as part of that, we did some experiments using different pressurized conditions and inlet values for the temperature. And as you can see, as we increase the pressure, something that was and has been documented and also traced, is that the pressure will reduce the NOx emissions that we got substantially. So pressure combined with these stratified conditions, with this post-combustion treatment, could be the solution to those NOxes that we're producing. Here, for example, in this case, what we got is is now at 3 bar pressure, a massive reduction going from the thousands to these values that will run at high temperature inlet conditions. Similarly, you see how the trend starts flattening down, and this is a combination of 75-25 ammonia. Again, this based on some of the requirements from our industrial partners, but it shows that trend of how it's going down. So this is what you would expect from numerical analysis. Then a reduction when you have ammonia and hydrogen, and then similarly, as you start increasing the temperature, obviously, that will increase NOxes. But in a combination of both pressure and temperature should then tackle this. So this is some of the studies that we have done in collaboration with Baker Hughes, and they show how these trends actually just can be replicated in some numerical modeling. This is so far who we believe and we know that are already playing this agenda in gas turbines. If you know of someone else that is not there, please let me know. But essentially we have 3 different phases, the way that we see it, very fundamental. The one that is just setting up all the systems and experimental conditions, just to start running conditions and combustors, and then finally gas turbines already running. Only 2 players, as we know, KAUST and ICE doing the phase 3 research. So all of them are moving in that direction, and now one that is picking up very quick is obviously China. Another topic, propulsion, is an interesting one. I'll just focus very quickly on this one because Russia, China, UK, European countries, etc., have actually tried for very small propulsion systems in satellites. Now, we did a study for how much would be a same tank running on jet fuel, liquid bio mass, and ammonia compared to hydrogen. And you can see that the case of the hydrogen is the worst for all of them. Again, based on that energy density that we're talking about and having exactly the same amount of volume for the cases here. Another study that was really interesting was the one done by Coleman. And what they did after doing some analysis on all these different thermodynamic parameters, then a table showing all the different properties of jet fuel compared to all these different options. And one of the things that comes out that was really interesting was for ammonia and ammonia hydrogen, the toxicity. So toxicity is, according to them, one of the major issues, and actually it is. But again, it's something that, although it is not producing any problem, it could in the near future when we have a fuel-based ammonia system. And one of the main problems when we talk to our industrial partners is that they say, well, when ammonia can be used, it's, again, you have shown it's possible, but at the end of the day, we have untrained people using it and then fueling tanks, that can be an issue. And again, you could then talk about the cases in Minnesota, in the US, where this is done by farmers. So again, it's a case that is more on the rounds around the public perception. So on those lines, on manned vehicles and also reaction engines, looking into this point, as I mentioned as well with NASA, how then that can then use ammonia to then redistribute this hydrogen. And finally, on the public perception side, one of the things that was interesting on the study that we did was to then evaluate developing and developed economies. And surprisingly, once that you talk to developed economies, the main problem is the smell. Whereas developing economies, it's actually the toxicity, because again, of regulations that are different. Ammonia lines and ruptures known, very well known in the developing countries, where towns, entire towns, get affected. Whereas in the case of the developed economies, where all the training with all the regulations are much better, then this is not the case. So again, it's got to do more with the public perception and also how we follow the regulations in each of the countries. These are some of the collaborations that we got. Many of you are here, so thank you very much for making this possible at different scales that we got. And these are just some of the things that we get ongoing, as mentioned by Professor Mohi, the book that we got, a journal on ammonia technology, and then 2 big symposium, the first one, the ammonia energy in Orleans, and the second, that is the combustion meeting organized by KAUST in Taiwan as part of ASPAC. So just as a conclusion, ammonia can be used to decarbonize all these different vectors, cooling, heating, power, propulsion. The problem is obviously the NOxes, the toxicity, the low reactivity, but there are processes, there are ways in which we can do it. Now the name of the game is to find the right one. Research is ongoing on all these technologies, in different scales, different industrial partners with different types of systems. And the idea is that if we want to get into a hydrogen from ammonia economy, then we need to work together. So that can then speed up this economic change. Thank you very much, and any questions?
Thank you very much for this actually very interesting presentation and for the exact timing. Very good. So we have 5 minutes for a few questions. Please.
From here, many thanks for your very interesting presentation. My question is about the global effect of the system, particularly because that ammonia can react with some atmospheric contaminants. It is responsible of many soot formation on the soot buildup. Do you have some analysis about that in your global view of ammonia possible use?
Yes, absolutely. That's one of the interesting bits. When we release ammonia, as mentioned in these cases, we have high ammonia contents, then can produce particle matter, soot formation. And one of the things is that as part of some of the studies that we're doing with Dell, we're looking into that spectrum. So we're starting with just a small city, a small location, using different agents, then based on the literature, and then trying to then find out what will be the environmental impact. But absolutely, if we want to have this type of systems running commercially, say a few years, 10, 20, we need to make sure that the ammonia is not coming out. Or if it does, it needs to be just well below the thresholds that we got right now.
Thank you, Goldie.
Yeah, thanks again for a fascinating talk. Perhaps focusing on NOx as a primary emission of ammonia is a bit misleading at this point, given that nitrous oxide is more likely to contribute to greenhouse gas emission than CO2. There's a massive difference between the two. And tiny amount of nitrous oxide from ammonia can kill the objective behind the whole thing. So have you looked at nitrous oxide and the different environments, especially in icy engines, and approaches to reduce its emissions?
Yes, absolutely. That is the name of the game, NOx emissions. Because just as you mentioned, N2O is 300 times, has 300 times the global warming potential of CO2. So if we just produce 100, 200, it's just as enough to then get rid of all these net zero, well, net zero, yes, but not climate change greenhouse gas. So absolutely, it is where everyone is working at the moment. Anyone doing ammonia combustion is trying to reduce those losses. Now, NO is the one that is mainly produced under rich conditions. One of the things that we have observed when it comes to the reduce quarters ratios leading conditions is that you produce the N2O. Now, that can be potentially tackled again with the pressure, probably something that we'll here in house and Gaetano, the guys working in there, can then do or are doing probably at this stage. But it is, as you're saying, the major detrimental. And that's one of the problems when it comes to industry. When we talk to them, they say, well, it's going to produce NOxes. So what is the point? You're getting rid of the CO2, but still producing the NOxes. And that's what we're trying to then go around it. And they say, well, it can be done at the combustion process to then bring down those NOxes if we do it clever and with the knowledge enough to then do so. Which again is what is going on. Yeah.
Okay, let's thank our speakers.